So welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, we say we do enjoy solving the harder problems, but above all, we do also see and appreciate the beauty in the simpler problems. So today, we are still on the MIT 2022 Integration B regular season trigonometry. So we shifted from part 2 that we covered last time. Now we're on part 3. And we have 3 very interesting problems in this session. The first problem is problem number 12 from the regular season, and that is the integration of sec squared into bracket 1 plus log x, that is natural logarithm, minus tangent of 1 plus log x, natural logarithm, that is, over x squared. So that is the first problem. Our next problem will be problem number 15, which is the integration of into bracket 1 minus cos x or cosine x, close bracket, to the power of 5 times cosine 5x. And that is spanning x equals to 0 to x equals to 2 pi. The last problem is problem number 17, which is a very interesting problem, which is an indefinite integral of 4 sine x plus 3 cosine x over 3 sine x plus 4 cosine x. So these covers the list of integrals that we'll be looking at today. So before I proceed, just a huge thanks to our subscribers for the amazing support they continue to show us. We don't take that support for granted. We are growing. We are elated about that. And also for first-time visitors, we would like to encourage you to subscribe to our channel. Your support will go a long way in giving us the extra visibility that we need to go forward. For those of you who are here for the second, third, fourth, or fifth time, haven't subscribed, again, the humble cry. We're sounding like a broken record, but we are requesting you to just pause for a second and subscribe to our channel. So going on to the solution, let's begin with that first problem, problem number 12, which is the second squared into bracket 1 plus natural logarithm x minus a tangent plus natural logarithm of x over x squared. So this problem can be split into 2 integral, and that is we have 1 over x squared times sec squared 1 plus log x minus 1 over x times tangent of tangent 1 plus log x. So as we can see, a sec squared is a derivative of tangent. Now, since we have a log x here, so when you differentiate tan plus log x, that is sec squared 1 plus log x times the derivative of log x, which is 1 over x. So how we could express this is this here, we've taken 1 over x, so it's 1 over x times the derivative of tangent into bracket 1 plus natural logarithm of x, and we've taken 1 over x to account for the derivative of log x, or natural logarithm of x, plus 1 minus x squared is the derivative of 1 over x. So here we see is plus tangent of 1 plus log x times the derivative of 1 over x. As you can see here, we can bunch these together since this format here tells us that this is the derivative of the product of these two functions, tangent 1 plus log x, and then 1 over x. So we can easily differentiate this as, integrate this as 1 over x times the tangent of 1 plus log x plus the integration constant. And this is the answer, a very simple problem. The next problem is a little bit cumbersome, but there is one important thing that it tries to teach us, and that is the principle of orthogonality between functions. So the integral of 1 minus cosine x to the power 5 times cosine 5x, we'll have to expand this to the power 5 term. And I'll use Pascal's triangle to at least get the constant, so which is 1, 1 for the first zeroth is 1, and then for the 1 is 1, 1, and then for the second power is 1, 2, 1, and then for the third power is 1, 3, 3, 1, and then for the fourth power is 1, 4, 6, 4, 1, and then for the fifth power is 1, 5, 10, 10, 5, 1. So we can consider this to be the first term 1, and then negative cos x the second term. So we can use these binomial coefficients to expand this term appropriately. So we have 1 here times 1 to the power 5 times negative cosine x to the power 0. So we have 1. And then 5 here, 5 times 1 times to the power 4 times negative cosine x to the power 1. So we get minus 5 cosine x. And then we continue all the way down up to negative cosine 5 to the power 5. And so we have all those powers. Now, for somebody who is intuitive enough, you could easily know that the only focus that one would, because if we multiply cosine 5x across, we'll have a certain combination of cosine functions. And we only want a term that does not amount to 0, since an integration of the cosine function is a sine function. And so you could easily know which terms would go to 0. But we're going to, just for the sake of clarity and simplicity, we are going to bulldoze through this solution. So we saw that just expanding 1 minus cosine x to the power 5 results into 1 minus cosine 5 cosine x plus 10 cosine squared x minus 10 cosine the cube x plus 5 cosine the power 4x minus cosine 5x. And then close bracket times cosine 5. So when you multiply cosine 5x across, so we have the blue term, which we are going to consider to be just the product of cosine 5x and 1, and then the green term, which is going to be the product of minus cosine x and the cosine 5x, and so on. So we have the purple, the green, the somehow it's not really orange, and then the yellow term. And so let's take the blue term as our first item to integrate, which is cosine 5x times 1, which is the integral of cosine 5x, and that amounts to 0, since sine 5x over 5, you plug in 2 pi, plug in 0, solve 0. Then we go to the green term, which is negative 5x, negative 5 cosine x times cosine 5x. So as you can see here, we can use the addition of the difference of two angles and sum of two angles so that we get the cosine term, and that's what we've done here. And since that usually amounts to twice cosine, the angles that are being added and subtracted, so we have negative 5 over 2 cosine 4x, because 5x minus x is 4x, 5x plus x is 6x. And so when you integrate cosine 4x, it's 1 over 4 sine 4x. When you integrate cosine 6x, is 1 over 6 cosine 6x. So these, when you plug in 2 pi and 0, that amounts to 0. So what this really means is that cosine x and cosine 5x are orthogonal. So when you multiply them and then you integrate, you get 0 from 0 to 2 pi. And then go to the purple term, which is 10 cosine squared x, cosine 5x. So cosine squared x is obviously cosine 2x plus 1 over 2. And so that over 2 cancels that 5, and so cancels 10, and we remain with 5 here. Multiply cosine 5x through, so we have cosine 2x times cosine 5x plus cosine 5x. And so this now results into half cosine 3x, cosine 7x, and then cosine 5x term. And obviously half here to account for the constant that usually is here, the 2 constant there. So again, we know that when we integrate these independent cosine terms, that results into 0, from 0 to 2 pi. And then the green term, the same way, if you want to figure out what cosine to the power 3x is, you can just use Euler's expansion, multiply by 3, power it to 3, and then you could use our famous Pascal triangle to obtain the constants there, the binomial coefficients. And as you can see, as you expand that out, we have the e to the power I3x and then e to the power I negative I3x. And this is obviously twice cosine of 3x, and this is twice cosine of x, twice 3 times the cosine of x. And so that is 1 over 8, 2 cosine 3x plus 6 cosine x. Plug that into our original integration. And so we have negative 10 times 1 over 8, 2 cosine 3x plus 6 cosine x times cosine 5x. So cosine 3x times cosine 5x. When you integrate that, we know that these are orthogonal, so that would be 0. And this also would be orthogonal, that would be 0. And the process continues. The fourth power as well, and you can use, again, Euler's expansion, power that up, and then you can use, obviously, our Pascal triangle to obtain these binomial coefficients. And then now you have the fourth power, the third power, and so on. And so when you combine that, we get cosine 4x plus 8 cosine 2x plus 6 all over 16. And then multiply that by cosine 5x. And then you begin to see that again, we come back to a point where we see 2 orthogonal functions that we multiply to one another and then we integrate. And so this entire integral results into 0. And so now we come to the fifth power, and that now is the term that we should have focused. And if you had intuition at the very beginning of the integral, you could just focus on that term, again using Euler's expansion, and then using obviously our Pascal triangle, obtaining that the binomial coefficient set. We can play around with the Euler expansion, and then we convert that into cosine 5x, cosine 3x, and then cosine x term. And as you can see now, there is an important term, and that is cosine 5x, that when we multiply by this cosine 5x, we do have a term that does not lead to a cosine function, and so doesn't amount to 0. So that is what we would want to focus on. So the integration of negative cosine to the power of 5x cosine times cosine 5x should be focused only on integrating the product of this cosine 5x and the twice cosine 5x here. such that we do have the difference of 5x and 5x is 0, so that leaves us with a 1. And that's why I have highlighted this integral as what we're going to focus on, and that is now 1 over 32, the integral of 2 cosine 5x and cosine 5x, and then 2 comes, we can pull 2 out, but that's not yet what we want to do. But we'll know that this is the sum of the difference of cosine 5x, tan 5x, and then cosine the sum of 5x, 5x is 10x. So this already, we know this would amount to 0. So we are left with just the integral of 1, which is x from 0 to 2 pi. So the sine term obviously goes to 0. So we have 2 pi over 32 as our answer, which can be reduced to negative pi over 16. And that is the answer. But it did require one to know the orthogonality aspect of trigonometrical functions. Our last problem today is going to be number 17, which is 4 sine x plus 3 cosine x over 3 sine x plus 4 cosine x. So this is an intricate problem. With this kind of problems, the surefire way of handling this is by substituting t equals to x over 2. Thus, dt dx is half sec squared x over 2, and therefore 2 dt over sec squared x over 2 is equals to dx, which means that 2 dt over 1 plus t squared, since sec squared x is 1 plus tan squared x. So we have 2 dt over 1 plus t squared equals to dx. So substituting that into the original equation, we have first of all to expand the sine x and cosine x term. We know sine x is twice sine x over 2 times cosine x over 2. So that multiplied by 4, we get 8 sine x over 2 cosine x over 2. And then 3 here, cosine x is the same as 3 times cosine squared x over 2 minus sine squared x over 2. The denominator, obviously, sine x is twice sine x over 2 cosine x over 2. So we have 6 sine x over 2 times cosine x over 2 plus 4 into bracket cosine squared x over 2 sine x squared over 2. Now, if you had a triangle and you use this triangular relationship where we had tangent t be equal to tan x over 2 with the angle x over 2 as the focus angle, tan is opposite of adjacent, so t would be our opposite, adjacent would be 1, and then the hypotenuse would be 1 plus t squared square root. So if our sine x over 2 is the opposite over the hypotenuse, that would be t over square root of 1 plus t squared, and cosine will be now the adjacent over the hypotenuse is 1 over square root of 1 plus t squared. And then the same process repeated here. Cosine is 1 over square root of 1 plus t squared, and that is squared since we have cosine squared x over 2, and the sine would be t over square root of 1 plus t squared square root, and then since we have a square here, everything is squared, and that process continues as shown here. And so we are left with now a 8t plus 3 into bracket 1 minus t squared over 6t plus 4 into bracket 1 minus t squared times t 2 dt over 1 plus t squared. And then we can multiply these polynomials together. And as you can see, we can also factorize them nicely, since 8t is the same as 9t minus t. So playing around with the arrangement of these components, we are left with the product of 3t plus 1 minus 3t, 4t plus 2, the product of and times 2t minus 2 minus t times 1 plus t squared. Okay, and so we can use partial fractions where we'll say for the first fraction is a over 4t plus 2. Second fraction is b over 2 minus t, and the last fraction is ct plus d over 1 plus t squared. Why? Because we have a quadratic term in the denominator. So one thing we could do is if we multiply across by 40 plus 2, and then if we substitute t equal to negative 2 over 4, 2 over 4, what ends up happening is that we can now remove the other constants, and we're left with a on the right hand side. And so in that case, a is equals to negative 14 over 25. Now the same thing if we multiply across by 2 minus t, and then if we set 2 equal to t, t equal to 2, and so the other terms, the other constant fizzle out, and now on the right hand side we have b, on the left hand side we now have a 7 over 50 equal to b. And then ct plus d, that term is complicated. One thing we could do is just by trying the surefire way of saying, okay, for this equation that we originally had, if we substitute 0 for t, what ends up happening is that we have 1, 3, 2, 2, 1 in the denominator. We have a over 2 plus b over 2 plus d. And so c has disappeared, but since we know a and b, we can now just substitute those values, and then we can then quickly move to the right d, and d is the same as 24 over 25. And then we could also just set t equal to 3 because we want to take the entire component on the right left hand side to be 0. And so we have 0 is equal to a over 14 minus b plus 3c plus d over 10. So when you continue playing around, you find that 3c is equal to 9 over 15 minus 24 over 25. And so 3c is equal to 21 over 25, which means that c is equal to 7 over 25. So we can go now ahead to plug those constants to our original partial fraction. And so what is easily visible here is that the first and second term could be integrated as a natural logarithm of the respective denominators. And the third term here could also be integrated independently. We could integrate this first and then use a natural logarithm, and then the last one we could use the arctangent as our solution. So here we can see that the integration is to cater for the 4 here. We have 2 over 4 times the constant that we already have in the numerator, which is negative 14 over 25, natural logarithm of the denominator. The same thing applies here. So we have negative 2, and since we only have negative 1 as a constant of this t here, that's why the sign changes. So we have this 2 multiplied by 7 over 50 natural logarithm of 2 minus t plus 2, and then considering this, 7 over 25 times half, that's half is to cater for the t squared, and times natural logarithm of 1 plus t squared. And then the last term here, this is a popular integration, 1 over 1 plus t squared is equals to, when you integrate that, is equals to arctangent of the t. So we can now simplify our expression. As you can see, using the rules of logarithm, we can combine 4t and minus 2t and then divided by 1 over t squared, divided by 1 plus t squared. And since these have the same constants, it's easy to just batch them together under one log function. And then plus 24 over 25 arctangent of t, right? So now we have these t values, and we know that t is supposed to be tan x over 2. So we can rearrange the t squared, which is, what we have here, and then substituting for where you see t with the tangent x over 2. And since we have an arctangent here, whatever we get here is x over 2, and this 2 is cancelled, so we have 24 over 25x as the integral of this term here, of the previous term. And then here we have 2 6 tan x over 2 plus 4 minus 4 tan squared x over 2 over 1 plus tan squared x. When we keep rearranging that, we get 6 sin x over 2 cosine x over 2 plus 4 cosine squared x over 2 minus 4 sine squared x over 2 over sec squared x over 2, since 1 plus tan squared x over 2 is sec squared x over 2. And then the denominator of this cosine of the tangent squared x comes here. So we have a product of sec squared x over 2 and cosine squared x over 2 in the denominator. And these also go and cancel each other. And so we have this term here that it seems like is going to be thrice the sine x. And then here we have 4 cosine x. And so that's what our answer is, which is minus 7 over 25, the natural logarithm of 3 sine x plus 4 cosine x plus 25, 24 over 25x. And that actually brings us to the end of our integral. Thank you so much for following along with us. But this problem seemed a little bit more intricate, but we were able to at least propose some solution or methods of arriving at the solution for you guys. Well, guys, if you haven't subscribed, please take a moment and subscribe. But it was an absolute pleasure hanging out with you.